Well, I would like to say a few words. I should say it in English because I want Horst and Oda to follow what I'm saying, and I wanted to thank all the people gathered here, and I shall refer to something that Yitzhak Herzog said during this first year after Yudah's demise. And he said that they were neighbors, and indeed they shared the same telephone line, and they used to leave each other little notes on the doors. And Yitzhak told me that he's sure that some doors will eventually open for me. And such doors indeed opened for me, but those doors, those openings, those opportunities, this strength, this inner strength that I had in order to try to open new doors, is only thanks to two friends here, and they support me and remember Yudah and Yudah's memory, and I'm sure that he is dear to you, or at least as a colleague, as he was to us, family. And I just asked the Guy Ron, if he ever met Yudah, and he said that unfortunately he didn't. So I really, it's a shame, because anybody who met Yudah knew what a wonderful person he was. And after Yudah died, I got letters from people who met him once, and they wrote me letters. What an impression he made on them. So it's a terrible loss for us, family, faculty, to the university. And I wish you all the best, and so you'll remember him this way at least.
Guy was a student of Professor Piasecki. He's a nuclear physicist, which is very appropriate. He's doing very well. Already as a student, he's a spokesman of an experiment in JLab, that we are flying soon, today. And he already has 5 PRLs published. So I think we're doing well here. Okay.
So those of you who came especially for the ceremony, but don't want to or can't follow the physics, you are welcome to. Yes, and we will now invite Professor Stöcker to his lecture, please.
Thank you.
So, we need to switch it on, I think. Is there a switch? Like this? High, low?
2 theorists.
Can you hear us here on the... Okay, it doesn't matter. Oh, okay. All right, just...
We'll try.
Okay.
Thank you. Ladies and gentlemen, very glad to be here to honor Yudah's 10th anniversary. We had an interesting discussion yesterday about lots of things, and I think I will be giving you a few impressions on how important Yudah was for our own institute in Frankfurt. Many people don't know that here at Tel Aviv. You think he was just here and did all he had and all his energy was spent on Tel Aviv. That's not true. He spent a major fraction of his spirits also in getting a similar spirit going as it is here. And you will see that this actually changed a lot in Frankfurt. One of the important things that he brought to us was a feeling for private engagement, private citizen engagement into a university. He worked really a lot together with community, which you know here also very well, of sponsors which are here in Tel Aviv, and brought together people, very important people, for us who are from your board of governance, who actually helped us establish with Wolf Singer and Walter Greiner, the Frankfurt Institute for Advanced Studies. I will walk you a little bit through this history. So the first 15 minutes or so will be devoted to memories to Yudah. And you see him here on an occasion of the 75th anniversary of our university, Johann Wolfgang Goethe-Universität, where he was one of the guests of honor because he was a member of our alma mater. This is actually the same year that he also got his Doctor Honoris Causa at Johann Wolfgang Goethe-University. On the right-hand side, you see his good friend Walter Greiner. And from these discussions over many years on how academic system could be put also on a privately funded basis, he got Walter here. He got Walter to discuss here with sponsors. He taught Walter how to talk to sponsors, and as you will see, this was really a very positive outcome. This is in the early 90s in Spain, where we had a conference going, and you see me here in young years over there with Park and Yudah in Walter's home in Spain. We had a conference on the nuclear equation of state, and I think then already we started discussing. We went on, had another NATO Advanced Study Institute in Bodrum in Turkey. Here, this on the left-hand side is one of my predecessors as GSI director, Hans Specht, and he was always working on people, get something going, which is similar to what we do here in Tel Aviv. Here you see a selected list of papers. I had only the pleasure of co-authoring one paper with Yudah very late. Actually so late that it actually appeared just before the first Yudah Eisenberg ceremony took place. And you recognize one gentleman here who at that time, you were dean? I think you were dean, right? No? Chair of physics at that time. And so this was one of the people which I mentioned before. You see here. Is this a... No, this is not a pointer. No pointer. I don't need a pointer. This gentleman here, this is Nikolaus Hensel, who was in your board of trustees together with Judah's brother, sister Nili, and the two people here in the middle is Reinhard Stock and his wife, Walter and Lichtenstadt. And they came for the bestowal of the first Yudah Eisenberg Professor, Laureatus as it's called, in 2001. And this gentleman here has actually been the person who endowed this chair, but he also started to work in this spirit. And what he did is he just assembled people in Frankfurt and said, well, you should do something which gives a new spirit to the Frankfurt system. Also talked a lot to our rector, who is actually in Frankfurt called President, Steinberg. And we got together this idea of privatizing the whole university system. And now, since 1st of January of this year, we are a foundation again. Frankfurt was a rich city in the hundreds of years where banks and dealing and wheeling were appropriate. And a lot of people actually contributed about 100 years ago to found Goethe-University. And in this old spirit, Yudah always said, you have to redo this, you have to redo this. And he infected Hensel and Greiner. And I will show you in a minute what came out of this. This is actually, again, Dr. Hensel. And you see here, again, Nili, myself, Walter, and our dean, who is now vice president of the university, Professor Asmus, in 2004, when we had the bestowal of the Eisenberg professorship again. And this came out of these activities. There's a foundation, the Foundation Girsch, which actually supported this idea of building a new theoretical science center. It's called the Frankfurt Institute for Advanced Studies, modeled after, we are long not there, but modeled after the idea of Princeton, that you have theorists in all kinds of theoretical science, theoretical biology, mathematics, theoretical chemistry, theoretical physics, and theoretical astro. And this just came up last fall. This is actually not yet finished. This was pretty much a year ago. Last fall, we moved in. This actually houses about 120 theoretical scientists from all over the world. It's about 50% non-Germans, 50% Germans, lots of graduate students, very interesting new enterprise. And I think FIAS would not exist, I'm sure, FIAS would not exist without Yudah having had such a strong impact on this whole spirit at Goethe-University. But one of the examples, Itzhak just mentioned this very briefly, where the theory has had little impact but helps to understand this whole idea, is the ion beam therapy, which had been developed by Kraft, Haberer, and Chart together with Debus from the Medical University in Heidelberg at GSI. The idea is extremely simple. You come in with a beam into a tumor of photons. Here is the middle of the head. The photons will burn through here and hurt your skin. So you have to have fractions from all kinds of sides. The photons will continue to deliver energy also behind the tumor. So it's a complicated issue how to catch a deep lying tumor. With heavy ion beams, this is different. Heavy ion beams, you get lots of delta electrons on the way out, but they are rather moderately influencing only your tissue. And at the place where the tumor is, you can direct your beam by using the Bragg peak property, and this is shown here. The energy loss of a beam with a given energy just has a very strong spike at the very end of the irradiation. And this way you can do sub-millimeter precision, actually slowing down the tumor growth, and with 10 fractions or so within a couple of weeks, 2 minutes each, no side effects. Lots of well-confined brain tumors can be taken care of. No problems afterwards, more than 90% healing rate. It's fantastic. And this was actually now studied intensively by Walder, Pshechnikov, and Mishustin at the FIAS. And we are going to the next round. And what you see, what came out of all of this is a huge tumor therapy program in Germany, which has been started, as I said, at GSI. We just finished 10 years. It was actually the same period as the time that Yudah passed away. First tumor patients were just gotten in when the sickness was developing in Yudah. Now, the ion beams have absolutely no side effects, nothing, 90% and more healing. It was developed at GSI. And the ion therapy clinics, which will be operational, is the first one now. It's ready in Heidelberg, HIT, Heidelberg Ion Therapy Center at the clinic. The second one, which will be ready in 2 years, is Marburg at the University of Marburg, a private clinic, and in Kiel, which just has been started, construction in Kiel. So I think with this we will be able to help also prostate cancer and other well-confined cancers on the level of many thousand patients per year. Every clinic here will be able to run about 2,000 patients, and with a 90% healing probability, you're of course safe with 5 clinics, 10,000 lives a year. It's really fantastic. Well, I got into contact with Yudah in the old days, in the 70s, when I started to work with Zev Frenkel and Yariv on microscopic simulations on relativistic heavy ion collisions. Yudah then was a frequent guest already at Frankfurt. And this is the only paper we ever authored together. This was actually authored after his death. You see here, 99. We were working on an idea which he had proposed together with Bernd Müller in the old days, the cooling of a quark droplet by evaporation of particles. And the whole gang here was inspired by this. This was the main result, that you actually are able to describe data rather well with this model, data in the sense that you get irradiation away from an equilibrated quark ball. This then transformed later on into a model which is called quark molecular dynamics, and you see here what is done is basically a Cornell potential which is applied to the to the quarks in a quark droplet. So that was the starting of a nice idea. Let me go from this more historical remarks to the future. The future for GSI will be a new facility which picks up these ideas and develops them into totally new areas of science where GSI had no active involvement till very recently. One area where we will go into much with the support of Russian, American, and French scientists is actually also a collaboration with the Weizmann Institute. Maron is working on this with us, is the idea that we can use a high power petawatt laser together with a heavy ion beam of dramatically increased intensity to create electromagnetic plasmas which are very similar to what you would need to come close to ignition in confinement fusion. So plasma physics will be a very strong new leg of these 4 legs of our table which we'll have in the future, and I will be very interested in looking into the strongly correlated aspects of this physics. Then we will have, in a similar manner, we will have the possibility of manipulating with lasers highly ionized matter and condensates in atomic systems. And you also all heard about this very interesting, although very strange, and Harry can talk more about this, Harry Lipkin can talk more about this than I can, phenomena which we found at GSI in the storage ring with this very interesting 7-second oscillations in beta decaying beams. This will be complemented by neutron matter studies which we do in the sector of very neutron-rich nuclei, which will be able to help us simulate neutron stars and supernova explosions. And from the last pillar, I will report a little bit also of my own work. This is Big Bang mass generation quark-gluon plasma, the first microsecond of the universe. You all know that this is a topic which is now very lively run at the LHC, at RIC, and we are actually going to participate into this endeavor also with this new facility. The facility's biggest change of what we have today will be enormous increase of intensity, primary beams by more than a factor of 100, secondary beams by more than a factor of 1,000 up to 10,000. You see here this short expression FAIR is this international facility. It's actually next to GSI. It's not a facility of GSI. It's its own company, which will be run by 15 countries, mostly EU countries, but also India, as you see over here, Russia, and China over here. And this spot we left free for Israel. Yeah, there is also Italy and France. They have made changing commitments. They have made a commitment, but it's not quite clear how much it is. With France, the usual commitment with France is, I shouldn't say this, but I say it anyhow. We'll give you 50 if you give us 100. And with Italy, it's a problem that, always the same thing, that they change governments quicker than we can get the letters there to be signed. Zitterbewegung, yeah, from the left to the right. So anyhow, this facility I will talk about now a little bit more is for several research highlights. I will only be able to touch upon the research highlights and make it interesting in the sense that we can talk about all the details later, all the details I know. What you see here on the left-hand side is good old GSI, the blue stuff. And I would need a stick or something to get there, I guess. Maybe I get, this is where the tumor therapy stuff is done. And you see a linear accelerator, a synchrotron, and a storage ring. This storage ring in the middle. Well, maybe this way. This storage ring is in the middle. This is where the experiments are done on the beta decays. Then there is a fence And there is a fence, a legal fence between GSI, this is the fence, and the FAIR facility, which will be here. And clearly GSI will stay a laboratory which is funded 90% by the state, by the federal government, 10% by the state, and FAIR will be funded 70% by German sources and almost 30% by international resources. Biggest contributor is actually Russia with 180 million euro. The total budget to build FAIR is on the level of $2 billion, 1.2 billion euros. So this will be complicated endeavor. I have no idea why they asked me to help get this going as a theoretical physicist, but it's clear that it's a lot of accelerator physics and a lot of accelerator gymnastics. Will be 8 rings communicating to each other, running. Oh, thank you very much. Thanks a lot. Yes, super. 8 rings running together with 2 linear accelerators. There's a new linear accelerator over here, which is a high-intensity proton LINAC. Then there is here the racetrack for antiprotons and also ions you can run in here of 15 GeV. And I will walk you swiftly through this. This is the old linear accelerator, the universal linear accelerator, where here the super heavy elements have been made. Element 107, 108, all the way to 112 were produced here by this old machine, which is almost 35 years old now. Then you inject into the synchrotron from 20% of the speed of light, roughly up to 95% of the speed of light. You see the 2 new synchrotrons are much bigger, so they will also get you to much higher energies. This is a 2 GeV per nucleon heavy ion facility. The inner one here will be a 10 GeV. The outer one will be an even higher energy, 30 to 40 GeV machine. This is the experimental storage ring where the oscillations seem to have been observed. These 2 synchrotrons out here in the FAIR facility will be ready in about 6 years. And their main goal with the CIS 100 is to go in a direct beam to this beam spot here, which is underground. The whole thing is actually 1.2 kilometers or so in circumference and about 15, 20 meters underground because of radiation safety. And here will be the most advanced high data rate detector, which one can imagine, which will be the CBM. We have about 400 users signed up to do this from all over the world. This is the CBM cave. As I said, it's deep underground. Then we have a rare isotope target over here, the next beamline, very high intensity, which will have a high energy beamline, a low energy beamline with traps. And then over here, with the proton LINAC, you can also introduce here the antiproton target and hit this. Both of these will be able to inject into these 2 rings, the collector ring and a recycled experimental storage ring or resurrected experimental storage ring, which will be using parts of this machine. From here, when you come in from the antiproton target, you will collect antiprotons, then cool them in the cooler ring, and then inject them here into the high energy storage ring, which is particularly interesting to make Hadron structure investigations, QCD and QCD in the medium. Cooled antiprotons will be extremely brilliant beam, up to 15 GeV over C. We have about 500 users for this facility, which will be here, the so-called PANDA detector, which will be particularly interesting to look for glue balls, for charmonium states. It's a community which you all know from LIA at the CERN accelerator. Now something is supposed to happen over here. Yeah, this is the super fragment separator. This will be from the rare isotope production target, also using the cooler rings and injecting into the next experimental storage ring, which, as you can see, is much, much bigger than this one here, and can circle very stably and also very far away from the synchrotrons, which is important. You never know what is injected in there. Then we'll have, in this nuclear astrophysics sector here, strange radioactive beams. As I said, also we can make very rare, very neutron-rich and proton-rich isotopes, which you can circle in here. And then we will have here the FLARE facility. Here's the name FLARE. Let me just skip this in. Flare facility here, we will have both naked, very heavy ions, so we can test ultra-high electromagnetic fields. We will be able to do lots of interesting atomic physics. Here are electron Cooler rings. So also here we can make collisions with antiprotons, with electrons here in the storage ring with cycling high-Z ions or antiprotons. You can capture the antiprotons, slow them down, and actually bring them to rest in flare. You can provide them with an anti-electron, and the positron antiproton pair can form anti-hydrogen, and you can actually trap them into a magnetic bottle. So there is one more very important field, I said it already before, is the warm dense plasmas. They will be having direct beam here, bunch compression, together with a petawatt laser, which will be installed here. We are already now, actually it's in this building, we have the so-called Felix petawatt laser, which just went into operation a week ago, where we can do heavy ion laser simultaneous beams on target over here. And we are thinking of having this also over here at the cis-18 to have higher energies. The problem there is we don't have enough compression of the beam pulses of the heavy ions. So if you shoot this beam into a solid state, it just explodes before all of the beam is in. So we cannot get enough energy done. That's why it's important that this machine now is upgraded to by about a factor of 100 in intensity and about a factor of 3 or so in down in beam duration, so bunch duration. So we'll come down to probably 70 nanoseconds or so. So then we also have material science and space and radiation biology applications. Material science also for space. ESA is very interested, just like NASA, because of space mission to Mars to test chip stability. So for this, they need cosmic radiation simulations, which we'll be able to provide. Now come to my hobby here. This is the analogy of the relativistic heavy ions to the universe. You know that the relativistic heavy ions at RIC here, for instance, collide. This is a typical collision at a high energy, fair energy, and the low energy runs at RIC. The two nuclei collide. Here is the overlap zone. They are relativistically compressed. That's why they are not spherical. And they have a lot of quantum fluctuations in the overlap zone. We have small configurations, large configurations. We probably have color transparency effects. Then for a very short period, less than a Fermi or so, we come into this initial lumpy initial energy density stage. And these fluctuations might also be starting point fluctuations, like here in the instanton model you see here, of fluctuations in the QCD vacuum. And then how these fluctuations get through this phase of quark-gluon matter existence into the hadronization and into the kinetic freeze-out and into the detector during the expansion and cooling of the system, we believe is similar to the strategy the early universe took. We think we can actually see evidence for such fluctuations in broad spectra of momentum distributions and also in particle yield distribution, kaon to pion ratios and so on. So this is very similar to transporting from this early stage, which is the Big Bang, through inflation up to the afterglow, like 400,000 years after the Big Bang, and then seeing still remnants of the fluctuations as we see them, and for which we got the Nobel Prize. This is, of course, not WMAP. That's before WMAP, Kobe. So the detector, which will be built for FAIR to measure this, to probe the high-density equation of state, to look for the fluctuations and to test chiral symmetry, is called the CBM, the compressed baryon matter detector at FAIR, and it will be able to measure charm, prompt gammas, thermal gammas, dilepton pairs, strange and multi-strange particles, and maybe even clusters of those, like multi-strange hypernuclei and so on. And you will, of course, see all kinds of hadrons, strange and non-strange hadrons coming out, decay gammas and decaying resonances. So this will be an interesting topic. This is this one big detector in the cage, which is most closely to the synchrotron. This is roughly how the detectors will look like I'm not a big expert in this. I just want to show you that the simulations show that we will be able to see the phi very clearly. We will be able to see very nicely the shape psi. And so this will be a vector meson factory, but it will also be a very nice Hadron facility. And in the CBM, we'll have a rich program near the critical point of the QCD phase diagram. We'll be able to do very low luminosity things with very abundant probes, but look into the tail of the stuff. And I just told you about the fluctuations as a signal. We'll be able to see rare events, the collapse of the proton flow, which could signal a first order phase transition. And we could look into fluctuations of this so-called elliptic flow. But also we will have the possibility with this increased luminosity, as I said, at least a factor of 100 of primary beam, very rare probes. We will see charm, quarkonia, D mesons, lambda C, and I think also heavier objects which are formed in the hot dense matter. And we'll be able to see dileptons. You know that this was not very well possible at the SPS. We'll be having a detector which can take much higher rates, and we will be able to look for something which Avram Gal will like, strange matter droplets and strange hypernuclei. Well, if you actually study this is done here in a work of Weber and Bravina using the ultra-relativistic quantum molecular model. I showed you before this simple model which we devised with Yudah like 15 years ago. This is a later development where you see the two nuclei which pass through each other, and you have here the colored fluid which expands, and you can measure what is the density here. Those are the colorless hadrons, those are the colored quarks. What is their temperature? You can analyze the temperature in such a cell by just analyzing, for instance, chemical properties or also spectra. And this is done in a lot of different models. I show you here a selection of 5 models. They all predict that in this very high intensity region, 20 GeV per nucleon lab energy, we will be able to get up to around 10 times nuclear matter density, 4 times, which are on the order of 5 to 10 Fermi over C. All the models say the same thing. But this is basically the two nuclei run into each other, and then you can just analyze what is the baryochemical potential, what is the temperature in this case. You see the temperature is roughly above the pion mass, and the baryochemical potential is about 1/3 of the nucleon mass. So that means you have very high densities over here, very low densities over here, so from 10 times nuclear matter density to 1/10 of nuclear matter density. And you freeze out, this we know from SPS data on very simple systems like lead here on 40 GeV and on 160 GeV. We freeze out actually our hadron abundances in this area. We also have calculations of the Wuppertal Budapest group and calculations of the Bielefeld Riken New York group, which indicate that somewhere here, if there is a critical point, somewhere here it should lie. So on the right-hand side of this critical point, we expect a first-order phase transition. On the left-hand side, we expect a transition passing over without having a real phase transition. And what we think is, according to these calculations, with this accelerator, we'll be able to just match these points very nicely, and devoting enough beam time, we should see the predicted fluctuations, and we should also see this effect of the phase transition on the collective flow which is observed. Now this is a very old thing, you see already more than 20 years old, discovery of the collective flow at the Beverlac, where you see flow angles when two particles, two heavy nuclei hit each other. This was gold on gold. They are smashed off each other by this hot dense collision zone here. It's like a spring which you have, and the pressure in this spring pushes the projectile and the target to large angles. And you see here, this was indeed observed, angles of 50 degrees or 40 degrees or something like this. And here you see the people who actually started this, Hans Gutbrot here and Art Postkanzer, who just got, when was it actually? 3 weeks ago or so, the Bonner Prize for this discovery. This is how Art looked when he came, when he was in Brookhaven. And here you see Reinhard Stock. He got actually just last week, it was announced, together with Walter Greiner, the highest nuclear physics prize we have in the European Physical Society, the Lise Meitner Prize, for the discovery, I mean Walter for the prediction, and Reinhard for the discovery of the flow. I think one shouldn't forget Hans, who was also heavily involved in this. Miklos, who was always trying to be honest, and this was me in the old days. That's actually when we started to think about ideal fluid flow. And this is our statement today. Ideal hydroflow might really be connected to some form of a simplistic idea of a conformal field theory, which allows us, and you have heard about this much, to connect very strongly coupled system in physics all over the place. And what is shown here is a simple experimental result, namely ultra-cold flow of lithium, which you see here, prepared with lasers in a very simple state at 10 to the minus 12 electron volts. Very nice elliptic shape. And on the right-hand side, you do the same thing. You prepare a very nice elliptic shape, not with lasers, but with relativistic heavy ions. And this is basically the old idea of Greiner in the 70s already, that then this matter should explode into this and in this direction. And what you can actually do, you can do a Fourier analysis and see how big is this anisotropy coefficient which comes out from such an initial state. And you measure this. Here is the anisotropy coefficient. We used to call this the bounce-off parameter. Now it's called elliptic flow, versus the transverse momentum of the emitted particle. And you see that for pions, for kaons, for protons, for lambdas, this is a strong ordering of this hydrodynamic flow. If you rescale this by the number of constituent quarks which you have in here, and you rescale also the transverse momentum, or rather the transverse kinetic energy, by the number of constituent quarks, it gives you a universal curve. All the lines go exactly on one line, and you see actually here hydrodynamic calculations predict this splitting. It's like a Zeeman splitting of the lines as a function of transverse momentum. So very, very hot quark-gluon plasma, 2 terakelvin. This is 10 to the plus 8 eVolt, if I was not mistaken. So many orders of magnitude different, shows exactly the same result as this ultra-cold lithium flow. And this supposedly is, that's the idea of the supersymmetric Young-Mills theory, all the same because it's all strong coupling, and this couples to this explosive dynamics. Now, this was put further on in last summer or so in Nature, even to the field of high TC superconductors. I'm not an expert in this, but again, via the same analogy, one seems to be able to connect this to ADS CFT. And for us, this is important because this means that our calculations with ideal fluids, perfect fluids, one should say, with very low viscosity, would actually be justified. We have looked into this viscosity over entropy ratios. They have been predicted by these supersymmetric models to be very small, 1 over 4 pi. Perturbative QCD has predicted 1 over 12, which is not so far away. But both are extremely small values. If you look up in the literature what is helium, what is nitrogen, water, and what have you, all these substances showed, in fact, that close to the critical temperature of a phase transition, there is a strong minimum in eta over S, but no measurement has ever gone way below 1. You see here, this measurement here is helium, it's around 1. Now the statement of this supersymmetric Young-Mills series, you would be at about 1/12, you would be 1/8, 0.08, I should say. And we have actually done calculations with Roy Lacey and Pavel Danielewicz, which actually shows that at least on the left-hand side, where we can use our old experience from heavy ion data, we get up to roughly eta over S of 1 in the Beverlag energy region, like 1 GeV per nucleon. And the higher our energy goes, the lower this coefficient comes. Then there is, of course, a big hole. We have no experience. And then we have put in the Rick number, which is very small number. And you see here, it's actually so small. The curves are just to guide the eyes. Then we might actually be experiencing in the T chemical potential plane that we are close to the critical point. We don't know really whether it's there, but the numbers which we have are so small that we could be there. There's, of course, also other interesting things to look for in this compressed baryon matter detector, like the disappearance of this signature of flow. This is an old standing prediction from the 70s already. The disappearance of the ideal hydro description in low momentum elliptic flow, and of course also disappearance of nuclear suppression of jets. And we could probe the system by resonances. We could look into hadronic lifetime measurements and chiral symmetry restoration. Long lifetime would, of course, mean you could see nicer signals of the rho and the A1. Let me just show you quickly an extrapolation which we did in Frankfurt. These are measurements of the so-called directed flow as a function of the bombarding energy. This is the old energies around the Beverlag and the heavy ion synchrotron at GSI, measurements here. Then here, these are measurements done at the AGS. And here are predictions, it's just a continuation of this line, from ideal hydro, which apparently has the wrong slope, but still shows that you should have this collapse of flow at negative values over here. And then up, and rising in the RIC low energy scan, which will be done in 2010. So this will be very interesting if really between here and there, no data existing, whether we really see this change in sign from plus to minus and back up to plus. This was done by Dumitru and Kerstin Pesch. He is now moving to, he's an assistant professor in Frankfurt, moving now to New York. And Kerstin Pesch was at the Perimeter Institute and is now in Stockholm. Well, good place to be for this. Anyhow, so this will be experiments which we hope to see as experimental data here and there. We'll see whether this goes. Okay, other fair physics is all related to this question of super high, super low temperatures, super high, super low densities. So I think with our new machine, we will be able to look into interior of planets, interior of the sun. Here is the planets. It's just shown down here. With our laser with heavy ion beam combined plasma physics, this warm dense matter idea, we will be able to store and cool ions to have actually Wigner crystals in the beam. So we can actually store very Coulomb-defined crystals. We'll be able to go all the way up to the quark-gluon plasma, and we will also be able to go into the direction neutron stars and see what cold neutron matter actually looks like. So it's really that we pull cosmic matter into the laboratory, and there are lots of analogies where we can learn and we can also exchange ideas with communities in astrophysics. For instance, of course, there are plumes and Rayleigh-Taylor instabilities who grow in supernova explosions. We will have exactly the same thing in this system I showed you before, this nuclei exploding because they are loaded so hot. And we have nuclear abundances, which are like in supernova abundance, and we can actually test nuclear structure effects, which lead to these very strange changes compared to the solar system abundances. We can have also hydrodynamic explosions of little plasma pellets here. I mean, this is, of course, not a plasma as long as you look at it. But then also in these pellets, you have these plumes growing and these Rayleigh-Taylor instabilities developing. So it's all a very, very closely related physics. The same, what I showed before, the vortices in the neutral Fermi gases, which have been observed by Ketterle et al. Here is Wolfgang, and Swearline, and so on. With the vortices on the surface, we can actually look into the neutron star surfaces where exactly the same thing is supposed to happen in the inner crust. So this will be very interesting to study vorticity, neutron stars, and cold Fermi gases, and so on and so forth. There's a long list of what kaon condensation and quark-hadron phase transition in neutron stars to quark stars, and so on, what can be done. Hans has written this already almost 15, 18 years ago, Pesek, Ravenhall. We will be able to do X-ray spectroscopy, very similar to the spectroscopy which you do on the stars, we can do on the material which we produce in the laboratory, which is star material. In the plasma physics, we can shine with the laser on material, hit with a heavy ion beam from the side, and then use this backlighter target radiation to really analyze what is going on in the material which we have under investigation, which can be very hot. We can do the atomic physics, as I said already, in the storage ring, can do X-ray emission studies in very clean environment. We can actually run single ions through the rings and study whether they decay and so on. We'll be able to do the multi-hypernuclei production with low energy antiprotons hitting into a nucleus, producing several strange quarks at the same time. For instance, producing cascade minus, this minus is supposed to be up there, plus 2 kaons, implant this into a secondary target, and then check what is the structure of a cascade minus or a double lambda hypernucleus. This will, of course, depend on whether the masses in the medium are shifted. If the cascade minus masses are shifted differently than the lambda, this might be in the nucleus a metastable state and not the 2 lambdas. So this will be interesting to see. This is the HyPi project, is hyperons in heavy ions, which here you see a time scale, should be running by 2014 with the Hypernuclear Separator. This, of course, will shed light on the interior of neutron stars. What is the consistency of neutron stars? Is it kaon condensations? Is it quarks? Is it all kind of hyperons in there? Or is it stable quark matter? We will see which of these opportunities will be realized in heavy ion collisions. Then very interesting complex for us will be the study of the physics program with the antiprotons. Very high intensity, very brilliant beam in this high energy storage ring, which I showed before. This racetrack will have an electron cooler on one side and the panda detector on the other side. So as I said before, we can do in this flare, which is the other detector a little bit to the right, antiprotons in traps, where we can study CP violation. We can do not only antiprotons, but also antihydrogen. But let me go to the, I think, very, very interesting idea of doing polarized antiprotons in here, which would allow us to study the spin structure of the proton, polarized antiproton proton beams. We can do lots of activities in this new accelerator, or rather storage ring and accelerator both. Particularly important for the PANDA collaboration at this time is in medium effects and shape size spectroscopy, very high-lying new states in the strange and charmed sector, also in baryons, and implanting hidden and open charm in nuclei. I find extremely fascinating the idea to study blue balls with higher luminosity than has been possible until now at Lear. And I think we will get clean signals if blue balls are not heavier than 4 or 5 GeV. If they exist, we should see them. This is the detector. It's a big machine. There you see a person, which will be closed. The antiprotons completely closed, fully 4pi supported. Antiprotons come in here. Then we have a target of liquid hydrogen, for instance, or liquid helium. And then you have forward time of flight and forward ridges, which will allow to study experimentally all the products which come out. Then here I go back to FLARE again. FLARE at FAIR is this antiproton decelerated facility where we can capture antiprotons in an atom and then slowly cascading it down into the nucleus. In the nucleus, there is a possibility that you get cold compression by deleting the vector attraction due to the protons in the nucleus, and then you would have p-bars in the medium with very interesting new possibilities. So All in all, this is a huge program. As I said, this is the old GSI. This is the new FAIR facility. It's a huge program which has key experiments in many different directions. Interesting aspect of this whole facility is all these experiments are capable of running in parallel. We can run at the same time beam in CBM and beam on New Star to test supernova elements, but also store antiprotons and study at the same time, really fully parallel operation in Panda glue ball production because it's a storage ring. We can store naked ions in Spark in the new experimental storage ring, which is another storage ring. And in the trap, we can at the same time here have, let's say, antimatter, antiproton with a positron combined to yield hydrogen. We can also do at the same time shots, which are not so frequent. We have typically 1 Hertz lasers then available, shots to make laser ion interactions to get up to extreme matter density. So this just shows you a little bit in the diagram how all these programs can be run in parallel if the machine is ready. This is the old synchrotron. This will be one of the 2 new synchrotrons. They're actually on top of each other. They just are shown like this to show all these different branches. Here you would have the radioactive ion beam program. At the same time, you could run the antiproton program in the high energy and the antiproton program at flare in the low energy sector. You run with the CIS 300 at the same time into the cave for CBM, the relativistic heavy ion program, and at the same time with CIS 100 feed the plasma physics cave, where here's the new proton LINAC. You go in, you can actually shoot with beams from CIS 18 and beams from CIS 100 at the same time and then add on top of this even a laser. So this really shows you that really in parallel, at the same time, you can run 4 completely different physics programs, which I think all have their discovery potential in different places. Some places which are really, I would think here, discovery of completely new states. Here, discovery of multi-strange clusters, discovery of the first-order phase transition point if it exists. Here, studies which are of very much interest as fundamental problems, but with a future in applied physics. And here for the RIA-type facility. We had a big start event. 1,400 people were there. You see down here with lots of politicians. You see actually here the politicians of those countries who signed. And unfortunately, Hans Gutbrod is very small, somewhere in the back. And Walter Henning, who initiated all of this, unfortunately was not able to participate. But it was a splendid perspective, and a really eminent challenge will come ahead of us. And of course, I strongly invite all of you to have with us participation in this physics program, and then look nicely on the Google Earth view of how FAIR will look in 2014. I'm sure Yudah would be smiling if he would see this, and that physics of hadrons and nuclei is alive and well and has a very strong perspective in the future. Thank you very much for your attention.
Thank you very much, Horst, for the beautiful lecture. And if there are any quick questions, please.
I have a question on the critical viscosity. In the literature of ages, it was stated that the viscosity actually diverges at the critical point.
Yes. Well, here, what you see here is data. And I think this is eta, and eta over S is 2 different things. I will go very quickly back to this. Do it this way. Oi, doesn't come quickly. Well, anyhow, eta over S is the important parameter. And now where am I? Here. Eta over S is the important parameter, and this is measured at the critical point. These are old, simple measurements of good old gases. I mean, this is just, I can even read it, water, good old water. This is nitrogen. This is, I think, the helium. And this only would be this fancy thing. You see, once you take eta over S, which is given here, you always have a minimum at this point. So it's important to divide by the entropy density. It's not eta.
It's fine. So you can imagine that if it is fine.
Yes. Yes, yes. I mean, these are data, which is actually from textbooks. This is not new measurements. The only new measurement is the estimate of this point here, which is at least a factor of 10 or so smaller than any measured fluid property we know. So if you accept eta over S as the parameter, this is a much closer to a perfect liquid than anything else observed until today in nature. It's the first time that you actually got way below eta over S of 1, way below. This is, I mean, you can argue maybe this is not 1 over 4 pi, but it's only 1 over 2 pi or something, but it's very clearly much below 1. No matter how you analyze it, you always get down factor of 2 in the error bar. I don't think, there is of course a big quarrel, but I don't think it's a reasonable statement at this point to say that because this value is so small, we have evidence for supersymmetric Young-Mills field. Because first of all, in supersymmetric Young-Mills field, where this result, or in ADS CFT, where this result was derived, you are not in the physical region. You are in a theory which is not really with the right number of colors and so on. Secondly, also recently it has been shown that you can expand and improve on the theory, and you can actually get below this value of 1 over 4 pi, even in the theory. So I don't think that we have discovered, or that we should make the claim that we have discovered a signature for supersymmetry here. Also, of course, the reason is that PQCD, perturbative QCD, predicts a very similar value. But one thing is clear. If this distance here is safe, we have seen the least viscous fluid in the whole world until today. And the statement would be, if this is true today, then also the early universe in the Big Bang, we had basically no viscosity or the minimum possible viscosity in the Big Bang. Very, very low viscosity fluid. Yeah, but as I said, there are now already first results which are below the 1 over 4 pi, about 1/2 of that value. So also you can look, of course, in the data. We will see whether this whole story makes sense, because if you look into the data for the LHC, you will see that in the LHC we should be way on the other side over here. We should actually get to higher temperatures, and we should be able to see higher viscosities again. Carsten Greiner has actually estimated this number in a higher order parton cascade with 2 to 3 partons and 3 to 2 partons, not only 2 to 2 collisions. And he finds that at the LHC, the viscosity will be, if this model is correct, double as high as at RIC. So it would be really a fantastic accident that we really see just at RIC this very, very low value. But as I said, it must not necessarily mean that this is the lowest value one can achieve. One has to look.
Thanks very much.
Thank you very much. Thank you for your patience. How much overtime did I go?